Okay, hi everyone. So let's try to prove this better than we did before. And by that I mean let's give a correct proof. So this is the limit of the sequence of partial sums. So let's take the mth partial sum from n equals 0 to m, a finite number, of what? X plus y to the n over n factorial. And let's just call that limit r. So that's a complex number. R is in the complex numbers somewhere. Okay, and then same for, let's say, s and t. So t is the limit of the sequence of partial sums. Y to the n over n factorial, n equals 0 to m goes to infinity. And similarly for s. Okay, and let's call the partial sums, let's call this r sub m, the mth partial sum. So r is the limit of the r sub m's. And similarly for the s sub m and the t sub m. So s sub m is what? The mth partial sum of x to the n over n factorial, n equals 0 to m. And t sub m is the finite partial sum of y to the n over n factorial. Okay. So what do we need to show? We need to show that the complex number r is equal to the complex number s times the complex number t. Okay? And first of all, by the limit laws that we proved, or that we could prove, if Sm converges to S and Tm converges to T, then the sequence Sm times Tm, where we multiply the partial sums together, that will converge to S times T. Okay? And so here's what we really need to do. Let's prove that for all d, or let's call it epsilon, for all epsilon positive real numbers, the absolute value of r minus st is less than epsilon. Okay, and what this would imply then, that would imply that r minus st is equal to 0, and so that r is equal to st, which is exactly r equals s times t, what we wanted to prove. Okay. Now, for this implication arrow, if you can think of this as just a lemma. If z is a complex number and the absolute value of z is less than epsilon for every positive epsilon, then that means that z equals 0, the complex number 0. And you could prove this by contradiction, if you like. Assume that z is not 0, then z is somewhere that is not 0. Well, then pretty clearly a ball of this radius, which would be the size of z divided by 2, would contain 0 and miss. It would contradict this. Yeah. So I mean, this is a positive number, and yeah. So we have a contradiction. Anyway, so this is how we're going to prove it. We're going to show that for all epsilon, r minus st is less than epsilon. Okay. So what do we need to do? Well, it turns out that the picture to have in mind is sort of, well, let's remember what r and s and t are. So r is, let's say this is a complex plane. Here's r. Maybe here's s and here's t. I don't know where they are in reality. That's t, that's s, and that's r. And what we're going to do is we know that we can put, for any desired sizes, we can put the r sub m close by there. Somewhere inside here is the partial sum. We can put t sub m inside of as close as we like, and also s sub m as close as we like. And so really, I mean, okay, let me draw this again. R is somewhere, r sub m is somewhere. Oh, and then actually, let's not do these separately. Let's have just, so by the limit laws, remember that the limit of the products of partial sums limits to the product of the limits. So let's say that R is here and ST is somewhere here. So this is not going to happen. In fact, R has to equal ST. But let's say they weren't equal. Then this would be the picture. Here's maybe R sub m, and here's S sub m times T sub m. And we know that we can put this as close as we like to ST within some ball of radius. And we know that we can put this as close as we like to R because of the idea of limits. But then what we're going to do is just observe that this plus this plus this is altogether, if you were going to walk much longer, or it has to be longer or equal to this. And this is the thing that we're going to care about, namely the size, the distance between R and ST. We're going to show that this is less than epsilon for every epsilon, okay? So then we're going to use this quadrilateral here to just basically say that R minus ST is less than or equal to R minus R sub m plus R sub m minus S sub m times T sub m plus S sub m T sub m minus ST. Okay, so this is, you can think of this as the triangle inequality applied multiple times, or you can think about it as the quadrilateral inequality, that any one side of a quadrilateral is smaller than the sum of the other three sides. 1, 2, 3. Okay. Now this we can make as small as we like. So we want it to be less than epsilon, so let's try to make this less than epsilon over 3. Let's try to make this less than epsilon over 3. And let's try to make this less than epsilon over 3. Because then together we would have that they are less than epsilon. And that is what we wanted to prove, namely that R equals ST. R equals S times T by showing that the size of R minus ST is smaller than epsilon for every epsilon, which means that R minus ST has to be 0, and so R equals ST, and that is what we're trying to prove. So now, why are these things true? If we can show that this, and this are true, we are done. So this is true if we take, if there exists, so by the limit, the fact that the limit of the R sub m's is equal to R, that implies that for every epsilon, and for every epsilon over 3, there exists an n1 such that m greater than or equal to n1 implies that R minus R sub m is less than epsilon over 3. Okay, so in other words, we can make this less than epsilon over 3 by going far enough out. Because, why can we do that? Because the limit of the R sub m's is R. Exactly the same way, because of the limit laws, the limit of the product is the product of the limits, we can make this smaller than epsilon over 3. There exists some n2, which might be bigger, and at the end, we're going to go past, the maximum. Let n equal the max of n1, n2, n3. Let's call this one n3 so that this one will have an n2. This one is going to be hardest. But anyway, so there exists n3 such that when m is past n3, that implies that Sm Tm minus St is less than epsilon over 3. For any epsilon we choose, we can choose epsilon over 3, and the fact that this limits to this implies that there exists n3. Okay. So that would give us this. We are almost done. You might think this video will be over in 1 minute. We just have to show that this is true. Well, we have to show that there exists some n2. Does there exist some n2 such that going past m2 implies that this is smaller than epsilon over 3? That this thing is smaller than epsilon over 3? So if yes, we're done. Because just take n equal to that, and then... But let's see here. How can we prove this? So let's look at what these things are. So what is this quantity? R sub m minus S sub m T sub m. So R sub m minus S sub m T sub m. We want to make this question mark less than epsilon over 3. And we want to find, does there exist an n2? That'll do it. Well, okay, so what's R sub m? It's the mth partial sum of x plus y to the n over n factorial, n equals 0 to n. And what is S sub m? S sub m is the sum from n equals 0 to infinity. Let's see. Well, because this sum is indexed by n, well, it doesn't really matter. So let's just see x to the n over n factorial. Then this is going to be multiplied by the partial sum of y to the n over n factorial. And we want to know can we make this less than epsilon over 3? Well, so let's look at this exactly. These are not equal, and so that is the problem. Let's actually look at the case, and this is frequently when you have too many formulas and you have no idea how to show something, then experiment. The experiment will be with m equals 3, okay? So then what's R sub m? R sub m is 1 plus x plus y squared over 2 plus x plus y to the third over 3 factorial, okay? And then what is this piece? Well, we have 1 plus x squared over 2 factorial plus x to the third over 3 factorial. And then this piece with the y's is just the same, but with y's. Now here's the problem. These are not equal. So let's look at what happens. So in other words, this is S sub m times T sub m, and this is R sub m. Okay. So, this is R sub 3, S sub 3, T sub 3. So S3, T3 is equal to, well, what is it equal to? Basically, it's going to give you R sub 3, but it's going to give you some extra stuff. So let's see what extra stuff it has. X to the third over 3 factorial times y. But okay, so what is it? It's going to give you all the things here, but then over here, you'll notice that nothing is higher than degree 3, okay? But over here, we're going to have degree 3 times degree 3, which will give us degree 6. So basically, there's going to be extra things over here, extra terms. Okay, and so what happens, and you should check this, is that we're going to get basically, okay, what are the extra terms? Well, first there's going to be degree 4 extra terms, and those will look like x to the third over 3 factorial times y, which is, this times this. That's going to be total degree 4. Let's switch to another color. X to the third over 3 factorial y. That's total degree 4. And what else is total degree 4? Well, here and here will give us total degree 4. So that's x squared over 2 factorial, y squared over 2 factorial, which is just 2, but anyway. And then also we'll get x y to the third over 3 factorial from here and here. That's the degree 4 terms. These are extra. Now, there's also some degree 5 terms even. This is horrible, but 2 times 3 will give you 5 factors. So what are those? Well, there's going to be x to the third over 3 factorial, y squared over 2, plus x squared y to the third over 2 over 3 factorial. And we'll just put some factorials. And then, is that it for degree 5? Yes. These are all the degree 5. And now, how many degree 6? Well, just one. Just this times this. X to the third over 3 factorial, y to the third over 3 factorial. Degree 6. And this is actually what S3 T3 is. In other words, you multiply these out, you're going to get R3. You're going to get everything here. But you're also going to get some extra terms. Okay? So, when we subtract them, when we do the subtraction, all of that stuff will cancel, and the only thing remaining is to show that this stuff in purple, copy, is size less than epsilon over 3. Can we show that? So you see what happened. We had Rm minus SMTM, but then a bunch of things are going to cancel, and only these extra terms went. But now, I mean, we had to figure this out in terms of m equals 3, but now what about for a general m? Well, there's still going to be extra terms. Okay, so in other words, how do we handle these extra terms? We have to understand them. So let's look at these degree 4 terms. This is exactly x plus y to the 4 over 4 factorial, but missing some terms. This is exactly x plus y to the 5th over 5 factorial, but missing even more terms. And this is x plus y to the 6 over 6 factorial, but missing many, many terms. It's actually missing all the terms except one. It only has one of them, but missing terms. But notice something here. This was R3. This was when n equals 3. The worst that we're going to get is degree twice m. Degree 2m is the worst that will happen. Right, when we do SM times TM in general, it'll be this biggest term times this biggest term, giving us one term of degree 2m. Okay. So now what can we do? Well, let's look. So instead of writing these like random terms and trying to come up with a formula there, what I'll do is I'll write this as sort of x plus y to the 4th over 4 factorial minus some other things. So in fact, let's just do that here. So minus some terms. So take that and we'll add this minus terms plus this minus terms. And now we have to figure out what those are. So this will take a moment, but basically in the end what we get is that R sub m minus SMTM is equal to the size of, well, take a sum from n equals m plus 1 to 2m, and then take x plus y to the n over n factorial minus, here are the extra terms. The extra terms are exactly, well, j plus k equals n, and j is greater than m, or k is greater than m, and xj over j factorial, yk over k factorial. And this is a sum where we sum over all the jk that add up to n, where but at least one of j or k is greater than n, and this is exactly what we get. Yeah, so we want to show that this is smaller than epsilon over 3. Okay. So this is going to be the annoying part. This part we know we can make smaller because basically because of the fact that the infinite sum of these will converge, and so they have to go to 0. So these things have to go to 0, and if we make m big enough, these start at m plus 1, so we can make those all small. In other words, yeah, well, hold on, let me explain this better. Okay, so Okay, I have some space underneath. So there's sort of two parts. So let's apply the triangle inequality again. This thing right here, we want it, is going to be less than or equal to, and let's first do this thing and then add this thing. So the size of n equals m plus 1 to 2m x plus y to the n over n factorial plus the size of, and now let's actually split this sum into well, let's not do that yet. This thing. And remember, we want this to be less than epsilon over 3, so let's make this less than epsilon over 6, and then we'll argue that this is less than epsilon over 6. Now, why is this less than epsilon over 6? Well, because this infinite sum, x plus y to the n over n factorial, converges. We know by the divergence test that the sequence of terms actually goes to 0. The term sequence goes to 0. And so can be made small if we choose m big enough, right? Because look at these terms. These terms here are only appearing starting at m plus 1. Okay, and why is that? Well, let's look back here. And remember that this was degree 4 because when we did the size of R3 minus S3 T3, all the degree m terms, all the degree 3 terms here were canceled from here. All the degree 2 terms here were canceled in here. All the degree 1 terms were canceled from here. The constants were canceled, I don't even know if there's constants, but basically the only remainder, the extra terms, were degree m plus 1, m plus 2, all the way up to 2m. And so that's why this sum starts at m plus 1, goes to 0. So there exists some n4 such that when m is greater than n4, that implies that x plus y to the m over m factorial is less than anything we want. Okay, so let's see. How many terms are in this sum? Because we have to make each of them. So there are m terms in this sum. It's a sum from m plus 1 to 2m. So like in the case m equals 3, it was a sum from 4, 5, 6. That's exactly m equals 3 terms, or extra terms. So, basically we can take this thing and say it's a sum of, it's less than or equal to the absolute values of each of its terms, plus some term, plus dot, 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 plus some term, where there are m terms, and any of them can be made smaller than, let's say, epsilon over 6m. Okay? So then there are m terms, and this thing is less than or equal to m times the biggest term, which would be the m plus first term. Okay, so I replaced the m terms that were each different. It started with an m plus first term, then an m plus 2, then all the way up to 2m. And so this one is the biggest. Why? And since by the ratio test, we know that this sequence is decreasing. There exists an n5 such that when n is greater than n5, it's decreasing. So it's, the sequence x plus this sequence is strictly decreasing because the ratios are less than 1, and the uncommon ratios are less than 1. To get from the previous to the next, you have to multiply by a number that's smaller than 1, so it's strictly decreasing sequence of terms, which means we can replace all these other ones by the biggest, which is the first, which is the m plus first, and so then this can be made smaller than epsilon over 6m, because the divergence test says the terms have to go to 0. And so then this part is less than epsilon over 6, because the m cancels the m. So anyway, we are now done with this piece. We know that we can make this term less than epsilon over 6. And if we can make this term less than epsilon over 6 as well, we are finally done, because then together they are less than epsilon over 3. And then all the way back up here, this is less than epsilon over 3. And then all these together are less than epsilon, which means that r minus st can be made smaller than epsilon for every epsilon, which means it must be 0, which means r equals st. And so one last thing to do is to handle this term here. Okay. Now, let's split this sum into two different ones. So let's look at it and say that actually it'll be less than or equal to, by the triangle inequality, something plus another sum. And so all these terms of all possible, we're taking all possible j and k integers, or non-negative integers, that add up to n, but where either j is greater or k is greater. And so, by the way, why is that? So let's look up here. Remember our example with degree, with m equals 3. You see that these terms here, we were missing terms. Wait, so here, these were the terms we got from S3 times T3, but we are missing terms from x plus y to the 4th over 4 factorial. And what terms were we missing? Well, for example, we were missing x to the 4th over 4 factorial, and we are missing y to the 4th over 4 factorial. And notice that j is greater than m. 4 is greater than 3, 4 is greater than 3. So, this x to the 4th and this y to the 4th will appear actually in this sum and this sum respectively, where either the j is greater than m, like the x to the 4th, or the k is greater than m, like the y to the 4th. And this works for the other ones too, like look over here. Here, this was everything in x plus y to the 5th over 5 factorial, except it was missing some terms. What terms was it missing? Well, it was missing the x to the 5th over 5 factorial. It was also missing the x4y over 4 factorial 1 factorial. It was also missing, so it had the next one, and then it was missing xy to the 4 over 4 factorial, and it was also missing y to the 5 over 5 factorial. And look at these terms. These ones have the degree of y greater than m. 4 is greater than 3, 5 is greater than 3. These ones have the degree of x greater than m. And so that's why we have this sum here. These are the extra terms. And so let's just split them into the the ones where x is greater and then the ones where y is greater. So here we have let's see, x to the j over j factorial, and it has to sum up to n. So let's take j greater than m, and then y to the n minus j over n minus j factorial. Okay, so I'm rewriting this sum. It's actually really tricky to do this, so you have to get good at this. But then here is the y's are greater, so that's the other sum. So k greater than m of x to the n minus k over n minus k factorial, and then y to the k over k factorial. Okay. All right. And this is, oops. Yeah, we're missing, so this is just the degree n terms. There's actually, there should be another sum here. N equals m plus 1 to 2m. Right, so we only need extra terms up to degree 2m. And so we are going to organize them by their total degree first, which is, oh yeah, here it is. So I forgot that sum. So now this sum and this sum together come in here. And so we organize it first by the total degree, starting from m plus 1, m plus 2, all the way up to 2m. And then at each degree, there's a bunch of terms that are included. Like here, there was, here in degree 5, there were these terms that are going to appear. And then we split them into those with x bigger and those with y bigger than m. So here we go. Let's include that. Sum n equal m plus 1 to 2m. And let's go just, I guess, j equals m plus 1 to n. And then we also need the sum over there. We need this one over here. N equals m plus 1 to 2m. And then we could say just k equals m plus 1 to n. Total degree n. Okay, so now we have actual sums. And so we want these to be less than epsilon over 6. So if we can make each of these less than epsilon over 12, and if we can make this one less than epsilon over 12, we are finally done. So why can we make them less than epsilon over 12? Okay, now notice that these terms, let's first just look at this, this term here. This thing starts at m plus 1 always. So if we make m big enough, and remember the sum of the xn over n factorial infinite converges, and that implies that the xn over n factorial themselves as a sequence go to 0. Okay, but if they as a sequence go to 0, then if we go far enough, there can be as small as we like. So we can make this as small as we like if we take m big. That is good. But then what if these get really big? So we need to sort of bound these. Okay? And also, there's not just one of these, there's many of them. There's the sum from j equals m plus 1 to n. And then there's the n going from m plus 1 to 2m. So here's the thing. If you look at this and you try to figure out how many terms in the sum, just like before we're going to have m terms in this sum, and that's why I took m and then replaced each of these by the biggest one, which was the first one. I'm going to do a similar thing here. So like a little lemma you have to show is that these sums have m plus 1 choose 2 terms. In other words, they have m times m plus, or m plus 1 times m over 2 terms in this sum. And also this one, they're basically the same. They just flip. Here the x is over m plus 1, and here the y is over m plus 1 in degree. And so we can replace, because these terms go to 0, we can replace each of these by the biggest one, which would be the first one, which would be the m plus first. Okay? So in other words, for just this one right here, we are going to say it's less than or equal to m plus 1 times m over 2. There's going to be that many terms times the biggest of these, which will occur when j equals m plus 1. X to the m plus 1 over m plus 1 factorial. Okay? And then the problem is that these are all different. And in fact, these can start and be very small. These can be like 1 or the exponent can be 0, the exponent can be 1, exponent can be 2. So we can't just say that these gonna go to 0 by the fact that that sum, we could if we make these far enough, but you see that we can't, these are not bigger than m plus 1. So this is a problem. So let's first think about the terms just of these. So in general, depending on what x and y is, these will start off, the 0th term will be 1, and then it might go up for a bit, and then it'll come back down and go to 0. This is now a graph of the size of y sub n over n factorial. And this is 0, 1, 2, this is n, and then this axis is the size of the magnitude of it. And it depends on what y is, exactly what this curve is. For some y's, like for a y that's really small, it might actually just start going down right away. But for some y's, like a big y, sort of like if we took y equals 50, or y equals 50i, same thing because we're taking absolute value, then actually it would start at 1, and then the second one would be up at 50. So you see that they can go up, and then 50 squared would be the second, it would be even higher. And so at first it's going to go up, but eventually it's going to go down and go to 0, because the infinite sum, y to the n over n factorial, converges. And so by the divergence test, the terms have to go to 0. And so I guess what I'm going to say is let L, so let's replace each of these by the worst case it could ever be, which would be this one, L. So we're going to replace these, all of them, in each of these m plus 1 choose 2 terms by y to the L over L factorial size. Okay. Where L is the index maximizing y to the n over n factorial in size. Okay, that does exist because these go to 0. So there is some biggest peak. It could be, L could be 0 if y was small, like if y was 0.1. Then this would be 1, and then the next one would be 0.1. Okay. So anyway, let's look at this thing. First of all, the m plus 1 and m will cancel, and 2 of these factors, and so we're going to just remove 2 of these and put it x squared over 2 x to the m minus 1 over m minus 1 factorial, whatever, y to the L over L factorial. So now, here we have something that goes to 0. Goes to 0 if m big enough. If m big enough. So let's choose m. No, sorry. Let's choose n. I'm not sure which one. n6, such that if m is greater than n6, we have this thing smaller than what? Okay. We wanted this to be less than epsilon over 12. So we want this thing to be less than epsilon over 12. But then we need to divide by this, 2 over x squared, and this, L factorial over y to the L. But you'll notice that x and y are fixed, so this is a constant, this is a constant, L is a constant, it's whatever is maximizing for that particular y. 2 and 12 are constants, and so this can be done. This is a positive real number. And because the exponential converges, the terms go to 0, and we can choose m such that this is smaller than this. And then we are done. We are actually done, because the other side, this term, is identical, except x and y are switched places. There are, m plus 1 times m divided by 2 terms. We'll replace, in each of those terms, they're a product. We're going to replace Now this time the y's are bigger than n plus 1, so we can make these go to 0. So we'll make them go far enough to 0, replace this with the biggest possible x to the L over L factorial value that this could possibly have, depending on x. So maybe you'd like a different name for this, L prime. Replace this with the biggest it can be, replaced all of these with the biggest possible, and so then we have the exact same thing as this, except y and x are flipped, and we can this time make the y's whose exponents start at m plus 1. If we make m big enough, these will go to 0, and we can go so far that they will be small enough to dominate the rest of these and make it less than epsilon over 12. And we are done. Okay. There's a lot to think about. So if you're really interested, I'm confident that this is correct, and you can try to work it out yourself, but this actually proves the fact that we need, which is this. And it does so using no fancy machinery, without any fancy math. Just adding, and I guess the quadrilateral inequality we needed. And we had to do some tricky things. They were definitely tricky. And the only way you could figure it out is by, seeing what is happening and see the extra terms and see how to organize them. And this is actually a pretty difficult proof. I think it's a difficult proof, this kind of a thing. So, you can check, does this actually represent, is this accurate in the case m equals 3? It is, and it's accurate in every case. So we have proved it. Okay, hopefully that satisfies anybody who is unhappy with my incorrect, wrong proof before.